Hello, good morning. Thank you for being here. It's a great pleasure to welcome you to Aymeric Ferron's PhD defense. I'm Anastasia Bezerianos. I will be the president of the jury. I am a professor at the Université Paris-Saclay, and I'm a member of a larger team of peers of the jury that will be asking questions after the end of your presentation, Aymeric. So I will be introducing them as they ask questions to save a little bit of time. So you will have 40 to 45 minutes to present your work, and then we will go into the question phase. Is that okay?
Yeah. Hello, everyone. Thank you for being here, and especially thanks to the jury for taking time today to evaluate my work. Today, I will present to you the work I've conducted about exploring concrete and immersive visualizations to communicate environmental impacts of daily actions. During these 4 past years, I've developed some visualizations going beyond conventional desktop visualizations, using, for example, some 3D interactive environments, some augmented reality, some virtual reality, and also some physical displays. So I will present you each of these projects, but first let me introduce what has motivated this thesis. The degradation of the Earth ecosystem through climate change and environmental pollution is one of the major challenges faced by humankind. Here are a few examples of dreadful environmental consequences. Deforestation, like in Indonesia, due to palm oil consumption, ice cap melting due to global warming, like in Norway, floods, like in Tuvalu Island, due to climate change, and also impact on biodiversity, like this turtle eating plastic due to plastic pollution. So in order to decrease our impact on the environment, humankind needs to change behavior individually and collectively. However, behavior change is really difficult to perform due to structural limits and strong habits. And this is not really the focus of this thesis. We rather focus on tools to communicate about environmental information because people feel like they are underinformed due to unpedagogical content. So one of the goals of this thesis was to design visualizations engaging enough to spark interest for the general public for them to interact with the data, getting a chance to learn about environmental impacts. To do so, we use concrete and immersive visualizations. We unpack what is it about. Some prior work investigated different ways to increase non-expert understanding regarding environmental impacts, including bridging the gap between raw data and more familiar and concrete concepts. For example, in this figure, each sphere is 10 meters wide and represents 1 ton of CO2. And here in the middle of Manhattan, you can see the daily carbon emissions of New York City. This work evokes a promising approach to represent data related to climate change, the use of concrete visualizations. Concrete visualizations are defined as a process of transforming entities that are usually represented abstractly into objects in space available to our senses. For example, typical concrete visualizations could be a stacking pile of money next to familiar buildings like the Empire State Building or the Statue of Liberty, but also like displaying some coffee cups next to a coffee machine, representing the cups used during one day in an office building, or also displaying some water bottles representing the water needed to flush a toilet tank. Concrete visualizations are useful when the magnitude of the data goes beyond humanly experienceable proportions, and also when observers are unfamiliar with the scales due to a lack of knowledge regarding the measurement used. So, moreover, immersive environments could be a good fit to extend the concrete visualization experience. For example, here, this is a work from Asso and colleague representing situated visualizations. But you could also have some virtual reality visualizations, like here's the work from Aymeric and colleague, where some air balloons represent the quantity of greenhouse gas emission in the sky. So in the next section, we elaborate more about how designers mix visualizations and immersive environments, a field known as immersive analytics. Immersive analytics is defined as the use of engaging embedded analysis tools to support data understanding and decision-making. For example, here you can see someone in VR grabbing 2 axes to create a new visualizations. So this is an embodied interaction. And here it's a visualization about it's a data visualization where people get to experience the heights of famous towers. So instead of just seeing the height on the bar chart, you get to explore this height in VR by walking around the towers. So immersive visualizations are useful for immersing people inside the data, to leverage embodied interactions, and it's currently increasingly used for environmental sustainability communication. So some studies suggest that immersive visualizations can engage people with data. This question was one of my main focus during my doctoral studies. We have several global research questions in this thesis. First, how can we represent environmental impacts in an engaging way? A question we addressed in section 3, 5, and 6. Second, what are the factors increasing engagement of environmental impacts visualizations? A question we addressed in section 3, 4, and 5. Then, are immersive and concrete visualizations a threat to environmental information credibility? A question we addressed in section 4. And finally, are playful immersive visualizations an opportunity to help people learn and remember about environmental impacts? A question we address is section 5. So we have seen that some concrete and immersive visualizations already exist in the literature to communicate about environmental impacts, like this one from Winrich and colleagues. However, representing directly an environmental impact with balloons does not really help understanding what could be the consequences on the environment itself. So we can ask, how can we represent concretely the consequences of environmental impacts? I tried to address this question in the first project using a mini world to communicate about planetary boundaries. This project has been published at the EHN 24 conference. So instead of simply visualizing environmental impacts, like the amount of greenhouse gas emissions or the amount of water consumed, we wanted to represent the consequences on the Earth. To do so, we use the concept of planetary boundaries. Planetary boundaries define the safe operating space for humanity and are associated with the planet's biophysical processes. There is 9 in total, and in this work, we are focusing on climate change, freshwater change, and land system change. What is interesting about planetary boundaries? That it represents budgets. Like, we are allowed to pollute a bit, but we are not allowed to pollute more than the Earth could absorb. So let's take an example with food and climate change planetary boundaries. Let's say planet Earth can absorb approximately 5 E12 kilograms of CO2 for our food budget during 1 year. If everyone on Earth would eat chicken every day during 1 year, the humanity would emit 1 E13 kilograms of CO2 in the atmosphere, so exceeding the budget. So planet Earth could absorb a part of this greenhouse gas emissions, but the exceeding part would stack in the atmosphere, and year after year, greenhouse gas emissions would stack in the atmosphere. However, let's say that humankind is all vegetarian. So here we are only emitting 4 E12 kilograms of CO2 per year. We are below the limits. It means that Earth is able to absorb all the greenhouse gas emissions, and then nothing is stuck in the atmosphere, and we remain at 0. So in order to picture this idea, we created a mini world which changes when humankind is exceeding planetary boundaries, like here, where the sea level rises across the years, and which remains still when we are respecting the planetary boundaries, like here. So we call this type of concrete visualization a proxy visualization. A proxy visualization is a concrete visualization encoding data through its impact on an object. So let's say we have an object in an initial state. We make the data vary. Then it produces an effect on the object, and then the object goes in the final state, which represents the data. Let's take an example with greenhouse gas emissions. Let's say that we have glaciers at the very beginning. Then when we rise greenhouse gas emissions, the temperature will increase due to greenhouse effects, and the glaciers will melt. So in the end, glacier volumes will decrease. Same thing for ocean. At the very beginning, we have a stable ocean. When we raise greenhouse gas emission, then the temperature increases, ocean expands, and glaciers are melting, and so the sea level rises in the end. So in our prototype, you can see here that when we travel in the future, you can see that the sea level is rising, and traveling back, like the sea level will decrease. And here, same for glaciers, when you go in time, you can see the volume decreasing. So here, a very important point, we acknowledge that we use highly simplified climate heuristics to represent this data. And this is not an actual modelization of the future of the Earth. I don't have time to unpack in detail, but here is a visualization for water use, like it's the level of the lake varying. And here we represent land use through deforestation. And here is the same thing. We also use some really simple heuristics representing those climate impacts. So we got different features in this prototype. First, people get to change their point of view to explore the mini world, to see the different types of proxy visualizations. Then they got to test different dietary habits. So some a bit caricatural, like here, where you could choose, for example, 100% beef, 100% chicken, like if everyone was eating the same thing every day. But here you can also compose your own menu, like choosing for 10 meals, the proteins, if you are taking some dairies, if you are taking some vegetables, etc. Then you got the time travel features, when you can go back and forth in time. Like here, for example, at t equal 40, we can see that the lake is almost dry already. And finally, the final features is meant to compare dietary habits. So here, for example, I put like eating fish for every meal at the right, at the left, and eating chicken for every meal at the right. And you can see here that on the right, sea level is rising a bit faster, so it suggests that greenhouse gas emissions, chicken emits more greenhouse gas emission than fish. So we conducted an interview with 3 experts. It was semi-structured interviews and along 2 topics, prototype content and usage scenarios. Then we ran a thematic analysis on these results, and we brought to light 3 topics: knowledge transmission, engagement, and usage scenarios, but I won't have time to unpack about usage scenarios. About knowledge transmission, some experts said that it was nice that we adopted a holistic approach of environmental impacts. Meaning that here, for example, this expert said, okay, this is a more global vision than just greenhouse gas emissions, because often when we are talking about environmental issues, we are focusing a lot on greenhouse gas emissions. And here we are also talking about fresh water and land use, so this was appreciated. Then some experts said that thanks to our prototype, probably that non-expert could get a qualitative information about what is happening. For example, here they would say, okay, beef has more impact than pork, so that's nice. However, those experts said, okay, but I will miss out anything that's more quantifiable, saying that I don't know what is the actual precise impact of beef or pork, for example. Finally, there is a problem about the underlying mechanism, so it's probably unclear. So an expert reported that I don't have an exploratory key. It's not obvious at that the ice is melting. Why is the ice is melting actually? So this prototype currently lacks of explanation. And we should explain what are the underlying mechanisms leading to climate change. So our proxy visualizations show potential to convey knowledge to non-experts about environmental data thanks to its holistic and intuitive approach of environmental impacts. However, a lack of explanation regarding the chosen proxy could be a threat for understanding, as well as oversimplified scientific models. Now, some results about engagement. So it has been appreciated that people could input relatable and personalized menus. Experts would say, okay, you could ask people, what do you eat? And then those people would answer that as inputs, and then they would test what are the impacts on the visualization. Then also, I noted an interesting behavior of one of the experts. She was projecting herself in the visualization. She was saying, okay, that I see a side to it, meaning that she was projecting herself at year 50 and not going further, because she said, okay, but I won't be there in more than 50 years. So she was really projecting herself in the visualization. And finally, one expert said maybe there is a lack of seriousness in the prototype because some audience, like for adults, maybe it's not serious enough looking to be taken seriously because it looks a bit of kind of playful, like a bit of video game. So we should definitely check, because if it's not serious enough, people won't believe the information. So our proxy visualization showed potential to engage people with environmental data through the possibility to input personal menus and to interact with the time projection. So we got encouraging elements about the potential of concrete visualization for engagement and knowledge transmissions. However, one expert raised an alarm saying, okay, but what about the credibility of information? If it's not taken seriously enough, people won't believe that. So before getting further with immersive and concrete visualization, we should definitely check if people think it's credible or not. This is the goal of this study I will present now. The project I will present now is an evaluation of the credibility of concrete and immersive visualizations of environmental impacts. This project has been published in TVCG and presented at the IEEE This conference. So in communication science, credibility is defined as the believability of information, interest largely in the trustworthiness and expertise of the information source or message. Credibility is important because it has an impact on behavior according to two social psychology theory, the elaboration likelihood model and the theory of planned behavior. So we could ask, what is the credibility of environmental information conveyed with unconventional visualizations compared to conventional ones? To answer this question, we run a study with 2 factors and 4 conditions. Our first factor is the visual encoding, either abstract or concrete. The second factor is the display modality, either desktop or immersive. We get 2 main conditions of interests: abstract desktop, which is a bar chart on a desktop, and concrete immersive, which is concrete visualization with AR headsets. And then we fully cross the factors with a concrete desktop version and an abstract immersive version. In the study, we showed 3 types of the data to our participants: carbon emissions, water consumptions, and also the PEF, which is the product environmental footprints, a dimensionless score, which is an aggregation of 16 environmental indicators. So when we need to represent abstractly the data, it's rather straightforward. We're simply using some bar charts. And so we are encoding the data in the length of the bar. However, when we are representing concrete visualizations, we need to find a semantic link between the data and the representation. For example, for water consumptions, I use some familiar objects containing water, like here a glass, a water bottle, a bucket, or a trough. For greenhouse gas emissions, since we are often communicating greenhouse gas emissions through their mass, we use some mass weight from 1 gram to 1 kilogram. Finally, for the PEF, Product Environmental Footprint, it was the most challenging unit because it's abstract by nature. So it's really difficult to find a concrete visualizations about that. So we use some unitization technique representing a little cube which represents 0.0010 millipoints and a big cubes representing 100 little cubes. And we have an animation of cubes falling down in glass containers. So we got several research questions. First, how differently the participants judge the credibility of concrete immersive compared to abstract desktop. Second, how engaged the participants feel with concrete immersive compared to abstract desktop. And finally, what is the difference in credibility and engagement across the visual encoding and the display modality? So we ran a study that we pre-registered on OSF. We got 32 participants. It was a within subject study, meaning that all the participants experienced the 4 designs with a different dataset for each. And the task was to follow an interactive data storytelling script. We measured several variables: perceived credibility, perceived engagement, perceived suitability, perceived persuasive intent, and some qualitative feedback, but I will only have time to report on the 2 first. Before continuing, I need to take a bit of time to explain how we computed our results with some Bayesian inferences. So instead of using some binary p-values answering the question, okay, does it work, yes or no? We rather use some Bayesian estimation answering to the question, oh, how well does it work and how sure are we? So we'll see all the results will look like that. I will have an axis with some values. Posterior distribution representing the probability of having the main effect size, having the Z effect size, sorry. A black bar representing the 95% credible interval, and a black dot representing the most likely effect size. So now, a few results about credibility. Here we can see that all the credibility scores are rather high overall. And when we look further, comparing AD and CI, we can see that it's centered at 0. So it means that we got no evidence for an effect. And since the distribution is really narrow around 0, we can see that the effect is likely small at best. Why so? Probably because all the designs were showing the same data, not the same data, but the data with the same source from a reputable source, governmental source. And also the information was easy to understand, and that we know thanks to the qualitative feedback. Second, we measured some engagement. So here we can see that CI is perceived as the most engaging visualization. And when we compare AD and CI, we can see that CI is considered as more engaging than AD. Finally, by comparing by factor here, we got no evidence for an effect of the display modality or visual encoding on the credibility. Everything is centered on 0. And for engagement here, we can see that we have a small positive effect of immersion, a greater a positive effect of concretes on engagement, and even a positive interaction between both. So now I will present a few limits about this work. Credibility is very difficult to measure because it's impacted by various cognitive characteristics. It really depends on the people, like people on the if they have flexible thinking, if they have self-confirmation biases, they have different types of attitudes, and our sample might not be really representative of the global population. So future work could extend the study to other participants. And then also I want to report about the specificity of our concrete visualizations. Of course, if we had made other choices, we would have tested other visualization, and the result might have been different. So future work should try to explore a bit more about those visualizations. So about credibility, we got no evidence for an effect, and the effect is as small. It suggests that the information credibility about environmental impacts might not depend on visual encoding or display modality, at least for the design we tested. And for engagement, concrete immersive can be substantially more engaging than other designs. So we got encouraging evidence of concrete and immersive visualization to be engaging and credible. However, in this design, the interactions were rather simple. So we are interested in pushing for more playful and open interactions, and to see maybe if it could benefit some memory aspects. So the project I will present now is an evaluation of enactment and quiz-based gamification on the memorability of greenhouse gas emissions. This project has been conducted in Finland as part of a scientific collaboration with the gamification group of Tampere University. And this project has been published at the AVA 26 conference and received the Best Long Research Paper Award. So our goal was to design a VR experience aiming to improve people's carbon numeracy. Carbon numeracy is defined as one's ability to approximate the correct value of one's carbon footprint without resorting to an explicit calculation. For example, if I ask you, okay, how much greenhouse gas emissions will be emitted when you are burning 4 liters of gas, you should have, if you have a high carbon numeracy, you should be able to say, okay, approximately X greenhouse gas emissions. In this project, we were interested in the carbon numeracy of several types of data sets, one about food and one about transport. For example, you could have several types of knowledge, 3. First, we could know how to order the item from the most polluting item to the least polluting item. We would say, okay, I know that beef emits more greenhouse gas emission than chicken, which emits more greenhouse gas emission than the vegetarian option. Then you could also know the ratio between 2 items. You say, okay, I know that beef emits 6 times more emission than chicken, and chicken emits twice more emission than vegetarian patty. And then you could also know the exact value for each of the data. And so we use also this data set about transport. The goal of the study was twofold: to see if people could learn about those data, and also, depending on the condition, if people could memorize better. So the question who drove us to this project was how to engage people with data in a memorable way. To do so, we decided to use some embodied interactions. In the context of immersive analytics, embodied interactions are defined as a notion that the affordances of a user interface or interaction device somehow naturally embody the purpose or nature of the intended actions. Let me explain with a project from Xu and colleague. So here is a visualization of 15 water bottles and needed to flush a toilet tank. In order to do so, you need to grab some water bottles in VR and to do the gesture of pouring the water bottles inside the tank. So making an embodied interactions, because otherwise you could just have to click on the button on the controller. But here you really have to do the gesture like you would do in real life. In the broad embodied cognition theory, there is the enactment theory. According to, they say that we understand the world through our body. And there is the so-called enactment effect, saying that enacted actions are better recalled than simple sentences. So we are interested in seeing if enacted interaction could maybe improve memorability. In this design, we use some these cubes, and people have to throw them in weighing scales in order to balance the scales. So here, one red cube represents 10 kilograms of CO2, and one yellow cube represents 1 kilogram of CO2. So here the enacted interaction is simply to throw cubes. On top of enactment, we were also interested in the benefits of gamification to support learning and memorability. Gamification is defined as the use of games across society, culture, and technology for purposes other than mere entertainment. Some studies suggest that gamification can support motivation and learning. So by adding a gamification layer, we wanted to test if it could help learn information and memorize it. So in our project, we decided to use quiz-based gamification. So for each order data ratio, it's a multiple choice questionnaires. If people got right, they got the correct feedback. If they got wrong, they got an incorrect feedback. If they got correct, they earn 10 points. And in the end, they got a final score, and they are ranked among other scores. So we got several research questions. First, what is the impact of enacting the exploration of greenhouse gas emission on memory fade? Then what is the impact of gamification on memory fade? And we were also interested in some engagement measures. And here we measured flow and intrinsic motivation. So what is the impact of enactment on flow and intrinsic motivation? And what is the impact of gamification on flow and intrinsic motivation? So we developed a VR experience where people are immersed in a room surrounded by weighing scales. Each weighing scale represents an item of the dataset. Here we use a metaphor of old-fashioned weighing scales. It's a bit of the same logic that previously, because we are often communicating greenhouse gas emission through their weight. So at the really beginning, all the scales are unbalanced. And then at the end of the experience, people will interact with each of the balance in order to each of the scales in order to balance them. The VR experience is twofold. First, a data exploration phase, and then a data visualization phase. First, and the data exploration phase is split into two subphases. First, people will discover the order of the datasets, and then they will learn about the exact values and the ratio between the items. And at the end of the data exploration phase, the whole dataset is displayed. And then for the visualization phase, people will interact further with each of the scales, making appear some cubes in the right pan to balance the scales. We created a study that we pre-registered on OSF. We got 63 participants. It was a mixed design study. And we got two factors, gamification and enactment. So for the gamification factor, it could be either high, so it's a game I was talking about with the points and the leaderboard, or it could be also low gamification, where here is just a simple walkthrough. People are moving around in VR, clicking on button to display the values. We have got also this enactment factor. So for the high enactment factor, it's just throwing cubes in the pan. And for the low enactment factors, people just have to click on a button to watch an animation of cubes falling down in the pan, balancing progressively the scale. So we have two factors and four conditions. The gamification factors only modifies the exploration phase, and the enactment factor only modifies the visualization phase. 50% of the participants got high gamification, then high enactments, and then high gamification and low enactments. And then the other half got low gamification and high enactments, and low gamification and low enactments. It was a mixed design study. We measure several variables, a knowledge score, intrinsic motivation inventory, flow, and also nasatelix, but I won't have time to report about the nasatelix today. The knowledge score was meant to understand how people learn. So basically, because every people is different, they have different kind of knowledge, so we had to ask them before the experience what they know. It's our baseline. Then they got through the VR experience. Then right after the VR experience, they're answering again the knowledge score, the knowledge questionnaire. And then we are waiting a few days, and we are measuring again the knowledge score to see if they forgot or not. Based on those knowledge scores, we computed some learning score, a short term measuring their initial knowledge with their knowledge right after the VR experience, a long-term learning score measuring their initial knowledge with the delayed knowledge score a few days after. And here, the bigger the learning score, the best people learn. And we also compute the memory fade score. So here, comparing the delayed a few days after with the knowledge right after the VR experience. And here, the bigger the memory fade score, the worse people memorize. So now we show a result about learning. So every result split. I'm making a difference between ordering the datasets and the ratios and the values because ordering seems to be easier. So here, for example, for the learning score, we can see for the ordering task that the effect is very large, so people are learning a lot immediately after their experience. And for the guessing ratios and values, we got a medium effect, so people are learning whatever the conditions. And a few days after, we got the same distribution, but a bit shifted to the left, meaning that people tend to forget a bit. So it means that participants learn overall whatever the conditions. Then a few results about the memory phase, starting with the ordering task. Here we can see, so here 0 means perfect retention. So we can see here we are rather close to 0, meaning that people memorize rather well, whatever the condition. And when we look at by factors, here we can see that all our plots are centered on 0. So I mean that we got no evidence for an effect by factor. Then for ratios and value, here we can see that all the plots are a bit shifted to the right, meaning that people have more trouble remembering. It's further from 0. People have more difficulties to remember. And when we look back factors, here we can see here for the gamification that the distribution is a bit shifted to the left. It suggests that we have slight evidence for negative effects of gamification on memory fade, suggesting that gamification might increase memorability, maybe. Why so? Probably because during the game, people were interacting intensively with all the questions because they wanted to have the right answer. So they spend a lot of time thinking to the correct answer. And then here, the distribution is a bit shifted to the right. So it suggests that we have slight evidence for positive interaction on memory fade, meaning that mixing gamification and enactment might decrease memorability. Why so? Maybe because the high enactment condition is really exhausting, physically demanding, and the high gamification is highly mentally demanding. So mixing both could lead to a task overload. Finally, a few results about intrinsic motivation. Here we can see that all the score are rather high, all above 0.5. And when we look by factors, here we can see that we have a small positive effect on the intrinsic motivation from enactments, but we cannot really conclude for gamification, neither interaction. And then about flow here, we got this kind of the same distribution. Everything is rather high, above 0.5. And here, when we look at the by factors, we got the same small positive effect on flow of enactment and flow. And we cannot really conclude for the other. So this work has several limitations. First, the knowledge task. So this work was inspired by some work of the literature about the ordering. Like the ordering task is rather common. Like in the literature, some scientists ask people to order item and dataset, but nobody asked people to get the data in the ratio. It was rather new, and so we had to create a new task. And the task has probably some limits. And some future works should understand the limits and maybe creating one which is better suited by collaborating with some people in the education field. And one limit about the degree of gamification, we could add that since everything looks playful and is in VR, everything is more or less gamified, and it's why we are really labeling our paper with quiz game gamification, but because it's really what we are testing. But even the quiz is rather basic, so future work could maybe improve the gamification aspect of this project. So participants learn information about greenhouse gas emissions for all conditions. About memorability, quizzes might have a positive effect on memory for the most difficult task requiring to remember ratios and values. And all designs engage participants, and enacted interactions seems to further increase this effect. So we got encouraging evidence of enactment and embodied interaction to increase flow and intrinsic motivation. So now the question is, okay, maybe we could engage even further people with effortful motion. And maybe using such interactions could support the understanding of data with huge differences. So in this project, I will present a proof of concept of a new type of visualization experience that we call AROM. This project has been published as a workshop paper during the IEEE Vis conference in 2025. So in this work, we focus on dataset containing orders of magnitude values that are dataset containing at least two numerical attributes that span 4 orders of magnitude or more. So representing order of magnitude values is kind of challenging because here you can see that if we are representing that with linear bar charts, small values are all flattened and we can see really differences. But the visualization researchers came up with a lot of different interactions tool and visualization, like here, a logarithmic bar chart. However, people tend to misinterpret log bar charts. So we could probably like stay with some linear bar charts, and we could maybe stretch the bars to see the differences between the lowest values. But in this case, like the big bar would exceed the top of the frame. And maybe we could use AR to stretch the bar outside of the limiting frame. This is the goal of an AROM, an augmented rumble along large orders of magnitudes. It's an augmented reality visualization. It invites people to rumble horizontally or vertically across several meters in the physical space. And the goal is to fully explore a dataset containing order of magnitude values encoding with virtual elements. So AROMs could have three goals. It could facilitate the comparison between small values, which might be flattened on other representation. Like here, we can see that the smallest value, we cannot see the difference between the smallest value. So we could stretch everything. And here, we can see now the difference between the values. However, here, since we stretch everything, we cannot see the top of the bars anymore. But it's okay because we can just look up and then we can see the bar above us. AROMs could illustrate the large difference in magnitude between different values in a visceral way, like here where the smallest values are on the ground and the biggest one reach the top of the atrium. And finally, we could also take advantage of the physical world features to support the data exploration, like here where the biggest bar reach the top of the building. And here we can see that even like all the other value does not even reach the first floor. So we present now a proof of concepts, timing charts. It's a vertical bar chart displayed in the inner building. So here you can see that the small value are really close to the ground and the biggest value like reaches the top of the building. So basically it invites you to climb stairs to progressively explore the visualization. So here at the third floor, I'm approximately at the middle of the visualization. I can see the bar and I can see also the lowest values. And finally, reaching the fifth floor, I can see the top of the bar, and here I am 20 meters higher than the ground floor. So what's interesting with ARM is that we have different options of designs. First, we could choose how to rumble. For example, you could have a really effortful way to rumble by asking people to climb stairs. It's really exhausting. Or you could simply put people in the elevator and then there is no effort anymore. And you could also choose where to rumble to have more or less impressive experience. For example, you could choose a really big location, like a big skyscraper, and displaying that the visualization over hundreds of meters, or hundreds of floors. And but also like a small location, like a 2-floor house, probably enough to represent also a basic AROM. So we didn't conduct any study about this work, but we have several questions. First, maybe this type of visualization could support the understanding of data and ratios through the embodied interaction of walking just next to the bars, because like you are moving across different distances and maybe you could understand, okay, now I feel like I walked twice more than before. And then we are also interested in the memorability of the data. Typically, by representing data with augmented reality, you could then align some bar with landmarks like the top of the building. And then when you remove the AR visualization, the next day, you could say, okay, now you pass by the building, you say, okay, I remember yesterday I saw this bar. I remember that this was this data that was huge. And so maybe it could trigger involuntary memories and reinforce memorability. So in this paper, I presented the climbing chart here, but we also presented an horizontal bar chart called walking chart and a walking scatter plot. Linked to that, we also created data ribbon visualization, where here you will extend the highest bar of visualization exceeding the top of the canvas, like moving around in the room. So instead of being linear, like in one direction, you could just really move in any direction you want. And finally, I also collaborated with Lenny Young, postdoctoral researcher in the VWAP team, on a design space covering different data representations and interaction techniques to represent data involving large magnitudes. So now I will present some perspective over the work I conducted during my thesis. The research introduced in this presentation paves the way to more concrete and immersive visualizations of environmental impacts. However, we did not properly measure if people understood better the mechanism leading to environmental impacts. For example, for the minimal prototype, some experts said, okay, but it's nice, but I'm not understanding what is happening right now. So maybe we could help ourselves with some storytelling, putting some characters in the visualization, some islanders, who could explain what is actually happening from an environmental point of view, and also maybe talking about the quality of life on the islands. So future work could answer the question, could storytelling support engagement and understanding of our visualizations? Then in this research, we introduced some gamification elements in section 5, where we focus on quiz-based gamification to communicate greenhouse gas emissions. However, gamification is much broader than just quizzes. So when we conducted some interviews with the mini-world prototype, some experts were saying, okay, but maybe at an input, you could ask people to manage resources on the island, putting, for example, some farms on some boat to catch some fish. And actually, this kind of games already exist in the game industry. For example, this one is Echo. The goal of Echo is to deflect an asteroid threatening the planet. And so you need to build a tool to deflect the asteroid, but without overusing the resources of the planet, because then you will kill the planet before the asteroid. A study suggests the eco game can promote environmental consciousness and foster learning. And moreover, VR has a great potential to leverage playful, immersive, and embedded interactions. During my doctoral studies, I collaborated with fellow PhD students from the team to develop an immersive and collaborative serious game called Trim, whose goal is to communicate about the internal functionings of trees and how they interact inside the forest to protect themselves from dangers. So we developed 4 VR mini-games, allowing players to activate biophysical processes of trees, but we did not conduct any study about this. So games are interesting because some studies suggest gamification help engage the general public with environmental topics, but there is one audience which is especially difficult to reach, people reluctant with sustainability. So we could ask, okay, maybe we could attract those reluctant people with gamification, and maybe they could learn and understand environmental impacts. Another way to engage people with environmental visualization might be to use effortful visualizations. In this thesis, we introduce this visualization requiring to climb 5 floors to reach the end, and also this visualization requiring to throw a lot of different cubes, and obviously, the bigger the greenhouse gas emissions, the longer you will have to throw cubes in the pan to balance the weighing scale. So maybe we could further extend this concept. In this thesis, I collaborated with Edwige Chauvert and Pierre Dragicevic on a physical prototype allowing people to carry the weight of their greenhouse gas emissions. As a proof of concept, one of the co-authors conducted a 14-day self-experiment during which they carried the weight related to their greenhouse gas emission of their meat consumption. To do so, they used homemade bags filled with rocks and sand, as well as wrist and ankle weights usually used in sports settings. While this experience was promising, some conceptual and technical questions remain in order to improve the design, such as ease the process of creating weights or decide on the optimal direction of weight carrying. So some studies suggest that some positive outcome of adding a thoughtful amount of difficulty when exploring a visualization, like favoring collective awareness, improving learning, triggering more mindful and conscious state of mind. So further future work should be conducted to better understand the advantages and drawbacks regarding engagement and comprehension of these effortful visualizations. Now I will present a few global takeaways about the full thesis. So our research suggests that concrete and immersive visualization can engage people with environmental data, support learning and memorability of the data, without threatening the perceived credibility of information. Meanwhile, our results call for nuance. Engagement does not automatically translate into understanding. Design choices, such as the level of abstraction of the degree of gamification, carry their own trade-off. And XR is not a silver bullet, and designers need to consider hardware or software environmental impacts when adopting such kind of visualizations. So this thesis supports the claim that moving beyond conventional representation toward more experiential and embodied forms of data visualizations opens a promising design space for engaging the general public with environmental impact data. Finally, I want to acknowledge how thesis isn't just an individual effort, it's a shared adventure, and a lot of people offered me the scientific and emotional support during the last 4 years. Of course, I want to thank my advisors, but also all my co-authors, as well as Anna, an intern I supervised during 3 months. I also want to thank all the Potok family, as well as the people I met in Tampere University during my 3-month stay. Finally, I have a thought for my friends from the GTGCGC and my friends from the AFRODIB. Finally, thanks to my supporting colleague from INRIA and to the members of the BOF project. Thank you all for your love and support. It helped me a lot during this research adventure. Thank you for your attention. I will be glad to answer to all of your questions.